Can you guys hear me okay? Okay. All right, so what I wanted to do in this next snippet of slides is to tell you a little bit about a particular application that we've been using BART for, particularly in terms of precision medicine and trying to identify which patients should get which treatment, trying to optimize in an individualized way patient outcomes. And this will mostly be focusing on not on the nuts and bolts of how to code things, but on the concepts and what kinds of things you can get out of BART. So the basic idea is that patients are heterogeneous and they may respond differently to treatment. And so the goal here is to, as I mentioned, is to identify which patients respond best to which treatment and try and tailor the treatments to individual patients. So essentially we're trying to look for a personalization based on the patient clinical features. It could include biomarkers, genetic information, and ultimately what we want to construct is an individualized treatment rule, or an ITR, which essentially is one that provides a therapy with the best predicted outcome for a new individual. And so if you saw Michael Kosarak's talk yesterday, he also was focused on identifying an ITR. This is a different strategy using BART from what he did. And I also had this up as a poster, but this will give you more detail and hopefully more information beyond what was in the poster, if you looked at that before. In some sense, this could be considered an extension of subgroup analysis, right? Subgroup analysis, you're trying to figure out a subgroup of patients that respond to a particular treatment. This is taking that kind of down to the individual patient level. And one of the advantages is this kind of personalized therapy can actually improve population health measures when you look at the strategy in terms of its population impact. So there are a couple strategies for doing this kind of thing. One is a policy search, and that's what we saw with Michael Kosarak's talk yesterday. There you directly optimize an estimator of the expected outcome of a treatment rule by looking over a class of policies or rules. The other option is just a direct predictive modeling approach of the patient outcome. And so one of the considerations when you do a direct predictive modeling approach is that you need good prediction accuracy in that model to get good performance of the ITR. And so this is where the flexible prediction models to handle those potentially complex interactions or relationships between treatment and covariates can be useful. So why BART? Well, it has excellent performance as a flexible prediction model. And beyond that, it also allows us to do something which a lot of the other strategies don't do as well with, is to actually quantify the uncertainty in a individualized treatment strategy, or the uncertainty in the benefit measure of an individualized treatment strategy. Okay, so just a little bit of the mathematical notation here. I'm going to describe this with the binary outcome of interest, where higher values or a value of 1 is desired. But all this stuff could be done with a continuous outcome as well. So we have got y of 1 is a good outcome, and y of 0 is a bad outcome. Treatments are essentially binary in this setting, but again, this could also be extended to more than 2 treatments. And then you've got covariates of interest x. And so an individualized treatment rule is essentially a mapping. It's a mapping from your x space, your covariate space, to the treatment A, so that a patient with a covariate x gets mapped to treatment g of x. Okay? So it's just a rule. It tells you input x, you spit out treatment A. Okay. So one of the common summary measures of a treatment rule is called a value function. That's basically what is the expected outcome if all of the patients were treated according to that rule, that rule G, that mapping. And so this value function can be written as a double expected value. It's an expected value with respect to the covariate distribution x of the conditional expected value of y given x and treatment A being assigned according to this mapping. Okay? So it basically says if you assign treatment according to this mapping, this is what your expected outcome would be across the population defined by x. So it is measuring a population impact of a particular rule or strategy to apply to the population. An optimal ITR G0 is one that basically has the best value function of any rules. So the highest value function or best outcome. And in fact, you can see that very clearly that this is true if the mapping itself is the one where the expected outcome across treatments is maximized. So if you for any given patient X, if you give them the treatment A that maximizes the expected value, that's the optimal rule in a sense. So that's what we're going to leverage to get a rule here, but using the BART model. So essentially, you want to assign each patient the treatment that has the highest expected outcome when you're doing a predictive modeling approach. So it's pretty straightforward. Now with the BART model, how do we summarize, or how do we develop a BART ITR? Well, as you saw today, the BART model basically says that the success probability is some function, and this is using a probit transformation. I also could use a logit. Usually an intercept, and then this function. So here now we're considering the function in terms of both x and a. So we're allowing it to be completely flexible in both x and a. And that function f is this sum of trees that you heard about earlier today. But in a sense, you want to view that function f as the underlying parameter that has a distribution as well. And in fact, each of the MC samples results in draws, FD, over across those MC samples from that function f. And we will leverage that a little bit later. So an optimal ITR, again, is the one where you choose the treatment, the value of A, that maximizes this expected value of Y given X and A, or the probability. So how do we do that? Well, we are going to use the posterior predictive distribution integrated over the posterior distribution of our function f, given the data. Okay, so that's where the posterior predictive distribution here is the integral of the conditional probability given x and a and a particular function f with respect to the posterior on f. And in fact, we can use our MC samples directly to approximate this integral. So if we've got our MC samples, FD, of the function value, we can apply the probit function here to get the probability given that FD and a particular treatment A at X. Okay? And if we average that across all of these samples of F, we get essentially this posterior predictive probability P bar of X and A. And so the BART ITR is basically the argmax of that P bar of X and A. So that's, you figure out what's the A. You do that for all the possible treatments, and you take the one, use the treatment that maximizes that P bar quantity for a particular patient. Any questions? Maybe I can pause there in case there's any questions so far. Okay. All right, so one of the interesting things that we can do essentially with the BART posterior samples is to make inference on the value function of any ITR that we want to use. So we've got any kind of mapping, G, or any kind of rule, G, we can leverage the fact that the value function of an ITR G is simply a function of F. Okay, so the value, we can actually capture a value function given a particular F. So we've got a rule G and a particular function value F, and this is just an expected value across the covariate distribution of the probability of success given X, your rule G of X, and a particular function value. Okay, but again, you want to think about F as being the random part here, or the part with the distribution. So we can plug in posterior samples of the value function, or plug in draws of F to get posterior samples of the value function here. So the value function is just V of G and a particular sample draw from F. Okay. Now, oftentimes, this does require an expected value with respect to X to get a value function. So, there are a lot of ways to do that. You can come up with your own covariate distribution if you want, but a lot of times in practice, people will average over the observed covariate distribution. Okay, so you take your observed sample data and the X matrix that goes along with that observed sample data and average across that distribution. So essentially what you get here are samples from the value function. So now we can think about the value function as a random quantity that has a distribution.
Hey, Brent, I just want to point out that that's what we were calling the Friedman's partial dependence function, essentially, averaging over the covariates.
Yes. Yes, except that it is applied to a specific treatment rule. So it is, in some sense, the Friedman's partial dependence function, where you're averaging over a covariate distribution, but you're doing it when you assign treatment according to this rule G of X. That's the only difference. Okay.
So it's like the counterfactuals that you're doing the trick on.
Right. Okay. So in fact, we can do this for any ITR, any rule G. We also can actually do it for the optimal ITR. The optimal ITR is, again, a function of this random F. So given F, we know what the optimal action is, right? The optimal action or optimal treatment is the argmax of the probability of success given covariate X, treatment A, and a particular F. Okay, so and this has a corresponding maximum success probability of P star of X and F, which is the maximum over A of the predictive probability given X, A, and F. Okay, so that's what the optimal ITR is. And in fact, the optimal ITR is, again, a function of F, right? So here's where if we think about F as this random quantity or a parameter, then we can work with that. So we actually can get the value function of an optimal ITR G0, again, is also a function of F. That value function is an expected value with respect to the covariate distribution, again, of this P star, this maximum success probability for a given F. And so we can get posterior samples of the value function by plugging in, again, these draws FD from the function F. Okay, so there's a lot of things that you can do with the posterior samples from that function F that you get out of BART. And so this really is all just post-processing of those samples. Okay. And so this actually quantifies the uncertainty about the value of the optimal ITR, and I put that random in parentheses because actually has a distribution. So the optimal ITR is actually not observed from this framework. The true optimal ITR, it's a function of F. So we have done some simulations, and I just want to show you how well this works. We generated ITRs using a training data set with a sample size of 500. And then we did two simulation settings. One that was similar, so I've got two references here basically, which you'll see at the end of the slides. But the setting 1 and setting 2 were basically simulation settings that came right out of other papers. So we didn't create our own simulation settings, we just used other people's stuff so that we didn't try and come up with the scenario that worked for us and not for anybody else. So we just used off-the-shelf settings. One of them was had 5 binary covariates, 5 ordinal covariates, and 1 or 2 continuous covariates, and the other one had just 3 independent continuous markers. There were a wide range of settings with no interactions, linear interactions, nonlinear interactions, varying link functions. Right? You've got your logit link, you've got your other kinds of links as well. So there are a wide range of settings, but I'm just going to give you a sense of how we performed across all of those settings. Each ITR was applied to a fixed independent test data set of 2,000 patients to determine the value function. So we know the value function because it's a simulation setting, we know the truth. And the average value function across 50 replicate training sets was used to compute the fraction of each ITR value function relative to the truth. So everything that you see here is normalized by the value function for the actual true optimal value function. And we did use cross-validation to select the number of trees, as well as the K parameter. Is that the notation you used earlier today? Okay. So we used a couple of values for the K parameter here as well with cross-validation. The competing methods that we looked at here, row SI, a regularized outcome-weighted subgroup identification, is an outcome-weighted learning type method. Outcome-weighted learning itself from the original method. We looked at random forests as just a prediction model where we cross-validated the number of trees and the minimum node size at the terminal nodes. And we also looked at a proposal that used boosting with a classification tree working model. So a number of different competing methods here. And this is the performance in setting 1. So you can see here the red is the BART with the default settings, black is the BART with the cross-validation. And for many of these settings, both of them are at the top, actually. The black one is slightly higher than the red one in a couple of settings, but almost indistinguishable otherwise. And there's only one setting, I think, where it dipped down just a little bit, but almost every other setting it was at the top or equal to the other methods. If you look at the scenario 2 settings here, again, the black is at the top except for, I think, just this one setting here, but otherwise, and maybe a little bit here, but it's generally at the top compared to many of the others. Random forest, which you might consider an analogous method to BART, was the green one here, so it's generally lower in many of the settings. The outcome-weighted learning actually really struggled with 2 of these settings. Did okay in some of the other ones. So it didn't win every time, but it was at or near the top pretty consistently across all these different scenarios. So it worked extremely well. The next thing I want to talk about is a little bit on operating characteristics of the of this method, and kind of how it performs in terms of prediction accuracy, bias. Can you really get intervals or can you really utilize the uncertainty of your value function estimation? So we demonstrated this with a sample size of 500 or 5,000 as a training set, and then prediction on an external test set, with either a complicated treatment interaction model or a no treatment interaction model, right? So if there's no interaction, does it still work, right? So where you're kind of you're doing overkill here, right? There's no interaction, but you're fitting this complicated model to it. Is it still going to perform well? So this first model, you can see here, this is the interaction term. It's got a quadratic in x1, it's got a linear in x2, and it's got like a tree type interaction in x3. So it's a complicated interaction model. The other one is not interacted. These are all logit methods. So we have, on the next slide, I'm going to show you some single data set predictions of the posterior mean treatment differences versus the truth, and repeated data simulation results as well. So you can see how it does with a single data set as well as if you average across repeated data sets. And then we also assessed the coverage of the posterior intervals for the value function, and those were quite good, 90% or 95% for the two different sample sizes. So if we have a large sample size, the coverage is right on. A little bit low with the smaller sample size, but also still very good. So this is the complex interaction model. And so you can see here with the single data set, which is on top, and the 500 is on the left, 5,000 is on the right. You can see, it's actually going to get a crick in my neck by looking that way. But so you can see that it matches. So this is the posterior mean treatment difference, and then this is the true treatment difference. So you want to basically see a diagonal, right? You want them to agree on the diagonal. And the single data set, it does pretty good. It seems to be a little bit low over here, a little bit low in this direction, a little bit low in this direction over here. With 5,000, that's pretty much resolved. If you average over data sets in a repeated simulation setting, you can see there is a little bit of bias in some of the tail areas or some of the extreme areas where it seems to be shrinking back a little bit, but that's probably not a bad thing actually. And then with the larger sample size, it pretty much nails the function. So again, even in the complicated scenario, it's picking up this complicated interaction, especially as the sample size goes up. What happens with no interaction? So with no interaction, basically everything is pretty much should be right here. There's some slight variation in the horizontal direction just because of the scale. This is on a probability scale instead of a logit scale. But otherwise, it should be right on there. And with a small sample size, you do see variability in the prediction in a single data set. With the larger data set, it's much smaller. So a little bit of variability in the predictive mean differences. As you average across the data sets in a repeated simulation setting, there's very little bias here. So it's matching up quite well with the difference. So it does well both with a complicated as well as a no interaction model in terms of finding what you want it to find. Okay. Now, one of the issues with a BART treatment rule, BART-based individualized treatment rule, is that it doesn't directly yield a simple interpretable rule here. Okay. So in some sense, it's a black box, right? You've got this g of x function, and can you explain it to clinicians? No. You can ask them for the x's, and you can spit out the g of x and the treatment assignment, but you can't explain to them what that g of x is. Okay, so it's a bit of a black box here. Right, so one of the things that we did was to try and figure out, is there a way to summarize or approximate the BART ITR in a way that is clinically interpretable. And one of the ways that we did that is to do the BART modeling, but then to do some post-processing, I guess, to try and approximate that rule. And this works well because we're doing separate modeling of the outcome from the determination of the rule. Okay, so all the inference is still valid, even if we do things afterwards to try and get an approximate rule. All the inference is done with the posterior samples, so we can still look at that new rule that we come up with and still make inference about it. Okay, so we're trying to develop an approximation to the BART ITR that is interpretable and has good performance. So this is a fit-to-fit strategy where what we do is we actually compute the posterior mean treatment differences for every patient. And we treat that as data. Okay? And now we try and fit that difference, that posterior mean treatment difference, to the patient characteristics. Okay? Now, not treatment, because treatment is out of the picture now. We've already taken differences between two treatments, so there's no longer a treatment variable to include in this second stage model. But we try and fit those posterior mean treatment differences as the outcome to a function of patient characteristics. But now at this point, we want an interpretable rule. So instead of using an ensemble of trees, we just use a single tree. So we're trying to figure out if is there a single tree that gets us a good approximation to the posterior mean treatment differences that we're getting out of BART. And we can assess that approximation by just simply looking at the R-squared between the single tree and the BART prediction model. Okay. So now I want to show you some examples of the kinds of inference and the kinds of things that you can do with that BART model from an individualized treatment rule perspective.
Brent?
Yeah.
Just so people don't misunderstand, you're not fitting a single tree to the data at all.
Right.
The original data, I mean, this is not a comparison of a single tree model versus the BART model. The BART model is the output. And then you're fitting the single tree to the treatment differences so you can explain it better. That's all.
Yes. And you may get a better sense of that when I get to the example and you can see what happened. It's a little hard to explain that without any actual data or something to look at. So that's why I wanted to go into the example and illustrate that point. So this is a bone marrow transplant example. So we do a lot of work with the Center for International Blood and Marrow Transplant Research here at the Medical College of Wisconsin. And this was a cohort of 3,802 patients that received a bone marrow transplant or a hematopoietic cell transplant between 2011 and 2013. These are typically done for hematologic cancers or malignancies like leukemia, lymphoma, those kinds of conditions. And there are a number of patient, donor, and disease factors that were studied here and collected by the registry. What we are going to focus on as our treatment of interest here is the conditioning regimen used, either fludarabine and melphalan or fludarabine and busulfan. And these are all the patient and donor and disease characteristics that we want to try and figure out, all right, which of them should be getting Flumel or which of them should be getting Flu-Bu in order to optimize their outcome and get an ITR. It turns out this observational cohort was actually pretty well balanced between these two regimens across all these different characteristics. So there does seem to be some equipoise by the clinicians, at least, in terms of which one they should be giving. The outcome here is 1 year survival, and we treat it as a binary outcome, mainly partly for simplicity, and it was feasible to do that because there was very little censoring before 1 year in this cohort. After 1 year, you start to see more drop-off in censoring. But we have pretty much complete data by a year. So we fit the BART model, right? Just like you would have done based on the rest of today. And that essentially gives us, our samples, right? For the probability that y is equal to 1 given a certain set of covariates, a certain treatment, and a certain function across those MCMC runs or samples. We can get patient-specific differences in one-year survival on a draw basis by taking the probability y is equal to 1 given x and a is equal to flu-mel for a particular draw, and the same probability, I'm sorry, I'm missing a p, for x and a equals flu-bu, and the same draw from the sample. Okay, so we can get inference, actually, essentially patient-specific inferences or differences in one-year survival right out of these samples. In some sense, this is a counterfactual, right? If you want to think about it in that way. You're looking at the predictive outcome for the two different treatment conditions for an individual. And we can plot the posterior mean of these differences for each patient, and that's what you're going to see on the next page here. I sorted it by the magnitude of those differences, so it's what we call a waterfall plot. You'll see those mean differences go steadily down. And then you also can, because you have samples, right, this is done for each of these FDs, each of these draws, you can construct interquartile ranges, 95% posterior intervals. So those are also shown on the next slide. And the other thing you can do, you also can say, well, you can figure out what's the posterior probability that flu-mel has a better one-year survival than flu-bu. Okay, so that can be obtained from those samples using this expression down here. So we're averaging across the draws of just an indicator, is the predicted probability for flu-mel for a particular draw bigger than the predicted probability for flu-bu in a particular draw. This is what these figures look like. And so these are individual patient inference, right? So each of the columns, it refers to a different patient in the data set. So again, we have 3,800 or so. So that's what the x-axis is here. And you can see the solid black line on the left is the posterior mean difference, and then the darker gray is the quartiles, and then the lighter gray is the 95% posterior intervals. So you see the quantification of uncertainty on a per patient basis. You also see the predictive values. And then on the right side, these are the posterior probabilities that flu-mel is better than flu-bu. And so, you can see that there's a chunk of people that seem to be benefiting from flu-mel. There's another chunk that is benefiting also, but maybe a little bit less. And there's another chunk that seems to be not benefiting from flu-mel. In fact, maybe benefit from flu-bu, from the opposite treatment. Okay, and you see the same kind of interpretation in this waterfall plot of the posterior probabilities that flu-mel is better than flu-bu. There's a chunk of people that have very high certainty that flu-mel is better than flu-bu. That's probably most of these patients here. Another one that has some likelihood favoring flu-mel, but not quite as strong. That's likely to be these in here. And then there's some that have a low likelihood that flu-mel is better down on the bottom.
Brent,
Yes.
is there a clinical reason why those patients fall off at the tail end? Did we explore that?
I don't know that you want to consider it a falling off, but it's a crossing of zero, indicating that the other treatment looks better for them. And I'll tell you where that's coming from. Yeah. Okay, so the other thing that we can do, so that was our individual patient inference. And one of the things that you see with the individual patient inference is those intervals are wide, right? In fact, probably almost all of them cross zero. So if you try and make inference on a single patient, you can't with certainty conclude that one treatment is better. Okay? That does not mean that you can't make inference about a rule. And so this next slide says, well, what if we have a series of rules for how to assign treatment to patients? How do those value functions stack up? And so this is a population type inference. This says, well, it's that expected value over the covariate distribution. And it tells you, well, what would happen to this population if we applied this rule to all the patients in that population, or all the patients in that data set of 3,802 individuals. And so I have value functions for 4 strategies here. One of them is just give everybody flu-bu. One of them is give everybody flu-mel. The third one is the BART ITR. And then the fourth one, the black one, is the optimal ITR, which again is something that is defined on a draw-by-draw basis and is not something that you can actually describe. It's not a rule that you actually can write down. But it is the optimal inference on the optimal ITR. And you can see the optimal ITR is close to the BART ITR, but not quite, but it's still a little bit better. Okay, so it gives you an idea of how close you get to the optimal ITR by using this BART rule. The other thing we can do is we can actually make inference on the difference in the value functions. So here we've got several differences against the BART rule. So this one on the left is BART versus optimal, and this indicates that optimal is better than BART, which it has to be. It's the optimal rule. But you can quantify how much better, and it seems to have a pretty high spike, very close to 0, so indicating that the BART rule is pretty close to the optimal rule in terms of how it performs for a population. BART versus flu-mel and BART versus flu-bu are both pretty much to the, favoring BART in terms of the difference in value function, right? BART is a higher value function than both of these other strategies where you just give everybody the same treatment, okay? Now, one comment to make here is the magnitude of this difference here, right? These are not big differences, and they probably reflect what you see on the left here. But one of the reasons that they're kind of small is that the difference, for example, between the BART rule and giving everybody flu-mel really only affects a fraction of the population, right? You can only move a fraction of the population to a better outcome by this rule. If you go back to these individual patient differences, basically you're moving these patients, right, with that BART rule, and saying these should be getting the other treatment, and so their benefits should switch. But all these other patients really are not affected by using a BART individualized treatment rule. They already got the better treatment. Okay, so you have to be a little careful about looking at the scale of the value function because it is a population-based inference, and because of that, the magnitude can be affected. Okay, so Raphael's question here was, okay, we've got a rule, what do you do with this? Okay, so one thing that we did with this is to try and come up with a approximation to the BART ITR. And so what we did was we took all of those, basically all the stuff on this black line here. For every patient, we took their posterior mean treatment difference, and we then tried to take that as the data, okay, and fit that to the patient characteristics to try and explain, basically the idea is to try and explain who are these patients over here, who are these patients here, who are these patients down here, okay, so we can interpret, what to do. And that's what this tree is, and we use a single tree so that we can get an interpretable result, and in this particular case, it actually ended up being a very simple split. The first one is on the disease, so non-Hodgkin's lymphoma versus AML, which is acute myelogenous leukemia, and other diseases. There were some secondary splits as well that didn't actually affect the direction, but they affected the magnitude of the posterior mean difference. This was on the aggressive B-cell subtype versus other subtypes of lymphoma, and this one was on the AML versus the other disease. And so you can see these patients over here, which are the aggressive B-cell lymphomas, they benefit from Flu-Bu to a degree of about negative 0.07. You can quantify the improvement using the posterior samples from BART. Okay, so you have a subset essentially, and you can quantify what their outcomes are. And these patients here, the other lymphomas, they also seem to benefit, but to a smaller degree. The AML other split, went to AML versus other diseases. And so there is a cohort of individuals that don't seem to benefit from either one. They're kind of a wash, or they're almost in an indifference zone. Very little difference here, but and then you've got the AML patients that seem to benefit from Flu-Mel. Okay, so we got a nice interpretable rule here. This is an approximation to the BART ITR. Actually, in this case, it actually matched up identically with the BART ITR, but that's probably an exception rather than a rule. So in summary, BART has excellent performance for defining these individualized treatment rules that optimize patient outcomes. It gives you direct inference on the value function of the ITR through those posterior samples. You can do the post-processing of that BART inference to provide these approximations that are clinically interpretable, and also hopefully have good performance, although you may not always be able to come up with that kind of approximation. So that's it for this. Any questions? Yeah.
Use a mic, please.
I have kind of a very specific question. I'm not sure this is the best.
Oh, you want to ask later?
Yeah,
Yeah, I'm
can I-
happy to talk it later.
Okay, thank you.
All right, let's take a 15-minute break and thank.
We have one more.
Where?
Go ahead.
I was just a little bit confused between the BART decision rule and the optimal decision rule, because at each of the DMCMC samples, you would get a BART tree and then permute the treatment equals 1, treatment equals negative 1, and then you would choose at that point
Yeah, so the optimal one is done on a draw-by-draw basis from the MC samples. So that one, it changes in a sense, right? The optimal rule changes from draw to draw. So that's not one that you can actually define or use, but it's more of a theoretical concept. The BART ITR is one where you actually use the posterior predictive distribution across all the samples. Okay, so that one, the actual expression for that one was here or, okay. So it's based on the maximum the treatment that maximizes the posterior predictive probability across the samples. So that's where you're averaging across the draws this posterior predictive distribution. Does that help? Okay.
Okay, so let's take a 15-minute break.